So how do we achieve something similar, this mapping function, in a deep unsupervised learning? Because here we're kind of assuming that the high dimensional data that we input is still, it's not as high as we're dealing with when we're dealing with deep learning framework and raw data. Rather, here we've assumed we've extracted some features already, either through a hand-engineered approach or set clinical features that we gather from patients already. So there's some legwork that's already been done, and then we just want to make it slightly lower dimension. Whereas in deep learning, we have a much higher dimensional space to begin with. So I want to start off with the most basic deep embedding framework, which is autoencoders. And autoencoders are similar to a neural network in that you have a series of layers and the output from one feeds into the next. But the purpose of the autoencoder is to take some sort of input space here, which is shown in orange, and map it to some sort of encoding or latent space, which is shown in green here. And the way we achieve this is by having a second part of the neural network architecture, which is normally a mirror of the first part of the network architecture. And the purpose of this part is to decode the encoding that is learned within our latent space and reconstruct the original input. So this is termed as the decoder, and the first part of our network is the encoder. And the way we achieve this in practice is by having a cost function, or a loss function rather, which compares the output from the neural network, which is a reconstructed input, to the actual input itself. So all of this is a reconstruction optimization task. It's learned in a fully automated manner, and it has a similar structure to PCA in that we're mapping the input to some sort of low dimensional representation. But what's different here is that we are introducing nonlinearity. And because we're introducing nonlinearity, it's really suitable for this raw data that we want to work with. And if need be, and if we know our data is fairly complex or very large, then we can add more layers in order to introduce more depth and to capture more abstract features if need be. So I mentioned that there are nonlinear manifolds that are learned within our autoencoder, whereas PCA we're kind of limited to a linear dimensionality reduction algorithm. And this image here kind of shows the benefits of the autoencoder over, say, PCA. And as mentioned, it makes autoencoders a stronger mapping function, which is suitable for raw data. I also mentioned that if need be, we can go deeper. And here we're actually seeing a diagram of a deep autoencoder, whereby our encoder has been expanded into 2 additional layers, and then those 2 additional layers feed into an encoded representation here. And then finally, we have another 2 layers, which are reflective of the 2 input layers, which make up our decoder. So you can see, whilst this is a deeper architecture, it still has the same framework. It still has the same task to perform, in that everything that is input into the network has to be mapped to a latent space. And typically, when we go deeper like this, we need to add ReLU operators as well, in order to prevent overfitting and other and to improve normalization and so on and so forth. And we also introduce sigmoid operators at the end to again help us achieve outputs between 0 and 1 as well. So when we train up deep autoencoders, we typically use something similar, which we saw earlier, which is the cross-entropy loss function, which is shown here for n number of instances and n number of classes. So if we extend that out for our autoencoder, really we have the reconstructed x input, and instead of having our y, which we had before, now we're just comparing it to the original input. So there's no need for any labels whatsoever here. We've eliminated the y term completely, which is a really nice property of deep autoencoders. So this here shows the PyTorch version of what I just talked about. So we have our optimizers, and we have some sort of loss function here as well. And you can see that the input to the model itself is just the image itself. There's no label that's coming from our data. That gets fed into some sort of model, which outputs our reconstructed X, our reconstructed image. And then that is fed into our loss function along with an image label rather than a label provided by the user. So really, this is how it works in practice. So if we compare the autoencoder and a deep autoencoder, and this is compared on MNIST, which is a popular data set, it's a popular toy data set, which is used in our field. You can really see what happens as we increase the depth of our network. You know, we go from slightly blurry images, which didn't have enough complexity to really capture all the digits in, accurately, to something that looks very similar to the original input. And if we go even deeper, we do get minor improvements, but because we're dealing with MNIST here, the improvements are very, very small indeed. And you can argue that the number of parameters you've increased by going through to a very, very deep architecture did not offer sufficient improvement in order to train X number of more parameters within this deep autoencoder. So those are kind of the trade-offs you make when you go deeper into an autoencoder, and it really is dependent on the task, depending on the size of the input, and so on and so forth, and the number of classes.
Can I ask a question?
Of course.
So the deep autoencoder, they are basically, just curious, it's fully connected layers, right?
Yes. Yes.
Okay. Thank you.
So that was a really good question and leads up to what I'm going to talk about next. And so previously we were talking about fully connected layers, but obviously we can use some knowledge from the deep learning field to enhance these autoencoders a little bit further. So here I'm showing you the same encoder-decoder architecture, but instead of having fully connected layers, here we're introducing convolutional layers, which are ideal for images and therefore ideal for MNIST. So here we're learning kernels, which can then be convolved with the image to produce some sort of output which has retained information about the translation and scale of the input image as well. So that gives us something, that gives us a representation which is more appropriate for our input data. So for those of you who are not familiar with convolutions, the idea is that you define how big these convolutional layers should be, how many filters you should have in a particular layer, and then these weights in the convolutional kernel are learned automatically the same way you would update a neuron as well. And then these get convolved with the input to that particular layer and then produce some sort of output for the next layer, and so on and so forth. And we can make this as big as possible to retain maybe some more context information if you need it, if you know your images are, say, really big and you need additional context. Or you can use other adaptations in the field, such as deleted convs to prevent overfitting, or if you know your data is noisy, you may decide to use deleted convolutional layers. And there are many other different types of convolutional layers that you can adapt and use. And here we're just talking about 2D convolutional layers, but if your data is 3D, you can extend this out even further. So there's actually a wealth of knowledge out there, and we can leverage that to suit each individual application as well.
So question, so if I want to learn more about convolutional layers, should I follow the link underneath the
yes, absolutely. Feel free to look at this. It's a nice high-level introduction to convolutional layers. I would also recommend the deep learning book by Benjio, and that seems to be a really nice way of going into the maths behind convolutional layers as well. And honestly, there's so much material out there that you could start off with the basic convolutional layers and then kind of make your way up to more specialized layers from there, depending on the field. Archive is a great resource, by the way, if you're working on a particular application and you'd like to know who else is working on similar work in your particular field, because you're likely to find specialized layers that are suitable for your data as well, by looking on something like Archive and searching in your particular field of interest. So lastly, I want to talk about sparse autoencoders before we move on from autoencoders, because it's a really nice framework, which again has a similar structure. We have an encoder and decoder, but in a sparse autoencoder, we're actually preventing chances of overfitting, which I'll talk about in a minute, but it's a major concern when we use autoencoders. So by enforcing some sort of sparseness within our model, we actually end up with a more powerful architecture and a more powerful predictor by switching off activations altogether. And we can achieve this in many ways, and it's usually done within the loss function and introducing, say, an L1, L2 penalization within the loss function. And there's many ways you can approach how you model a sparse autoencoder, again, by adding some of the techniques we talked about earlier.
So just to make sure I understand, so the sparse here comes from the fact that every time you run through the, I suppose this is doing training. So every time, or it's not doing, it's doing training or inference at the same time.
It's just during training, I believe, but I could be wrong about that.
So okay, so each time you sort of every step you sort of randomly mask, or every epoch or step you randomly mask some.
Yeah, that is exactly the idea. It's kind of, I like to think of it like dropout, but for your activations rather than for the neurons themselves. So the idea is, yes, to drop off neurons either randomly, or you can adapt your loss function to do essentially whatever you want it to do. But I would say randomly if I was implementing this myself.
Okay.
That way you're taking full advantage of all the neurons. You're just switching them off randomly for each batch, and therefore improving that chance of overfitting.
Okay.
So other applications of autoencoders are obviously denoising. So I think denoising was the very first usage of autoencoders, and you can really see why if your input is an image and the output is a reconstruction of the original input image, because your encoding should really learn what's essentially the key components within the image and drop all the noise. That's really the task that you're trying to perform there. Other applications which I did talk about in the Lunch and Learn is image inpainting, and I've given you some references here if you'd like to look at inpainting a little bit more, where we're getting a little bit more artistic within the models themselves. This is a generative model, so we'll get into that in a little bit, but we have encoders here as well. And some sort of hashing functions, which again makes sense because you're encoding the information, therefore a lookup table seems almost natural for information retrieval as well. So these are all applications that I'm not going to go into today at all, but you're more than welcome to go and have a look at. So I kind of touched on this a little bit earlier, but one of the biggest problems with autoencoders is that because that latent space is kind of free to do whatever it needs to do in order to optimize such that the output is a reconstruction of the input, we're not really helping it move towards a particularly intelligent way of performing that mapping function. So when we get deep autoencoders or deep autoencoders, that complexity magnifies. And as a result, it's very hard to really visualize what's happening within the autoencoder, even if we did look at the encoding itself. And it's very prone to overfitting because the latent codes can really be doing anything at all and not anything really crucial to the task at hand. It's not really figuring out what's exactly in the data and then figuring out the encoding part. It's rather going straight from data to data and just figuring out where this middle ground is. So sparse autoencoders help to mitigate this by avoiding the overfitting problem, as I mentioned earlier, it works in a similar manner to dropout, in that it makes sure that not a single neuron is kind of taking all of the weight within the network itself and accomplishing one or more tasks by itself, but rather that many neurons are working together. But there is another alternative to autoencoders, and that's going to be the next part of this talk. So we're going to touch on generative models now. So I did talk about this in the Lunch and Learn, but I want to go through it again. So generative models are great in that we're not just worried about this mapping function, but rather learning something intelligent about the data itself by modeling the data itself. And we can do this modeling process and learning some sort of probability distribution which represents that data in many, many ways. So the functions that I've shown here are Gaussian, uniform, and complex, but really there's an exponential number of possible probability distributions we can use in order to capture our data in a complex form. So today I'm going to talk about Gaussian representations, because we're going to go into variational autoencoders. But really the task here is that when we're given a random variable, we should be able to learn some sort of network representation which can recreate a new data point, and then that new data point can be can give us some sort of input. So first we have this modeling process, and then from this modeling process we sample some sort of another input, I guess, and then that gets fed into the decoder component. And that's what's different between the autoencoder and the variational autoencoder. So the variational autoencoder is similar to the autoencoder, but the latent space has a slightly different format. And that format is a series of unit Gaussian representations. And by enforcing that format, what we have is a latent space which is constrained in some way, shape, or form to kind of lie somewhere around the zero component within our high dimensional space, but with some degree of variation. So we're not restricting it too much, but we're also not letting it roam free as it was allowed to do in an autoencoder. And that makes it really ideal for generating samples, but maybe less so for set clustering or other techniques. But we'll see next week that we can still use variational autoencoders for clustering. We just need to adapt the loss function to do so. So this is great for highly variable data where you're not really sure if you've captured everything possible within your training set, and you want your model to be able to do something intelligent after you've trained it up and after you've deployed it out in the real world. So this is a diagram kind of showing you the variational autoencoder, and you can see it looks very similar to the autoencoder that I showed you earlier. We still have our input, our encoder element here, and our decoder element here as well. The only difference is the latent representation that we see in the middle. And you can see the latent representation is made up of that latent space here, but this latent space is composed of mean and variance of unit Gaussian. So we're learning almost double the number of parameters than we normally would do in that latent space. And then what happens is during training, instead of using this directly as we would do in an autoencoder, we actually sample a data point from there. So there's a kind of an indirect connection between the output from the encoder and the input to the decoder. And then that data point is then passed to the decoder to reconstruct the original input. And by having this almost slight divide between the unit Gaussian representations and this new sampled input, means that we're forcing our variational autoencoder to model something that looks something similar to our data, and then we're almost testing that modeled representation by sampling from it and then pushing it through our decoder. And this is another nice representation comparing an autoencoder here with the variational autoencoder, and you can really see where that divide occurs within the latent space and between the latent space and the decoder component. So because we've introduced unit Gaussians within our latent space, we need to adjust our loss function as well to account for the fact that we're going to have this modeling component within the middle. And this loss function is actually fairly simple and is made up of two components. One is a negative log likelihood, which is what you would normally measure within a neural network architecture if you were, say, given some labels. So it's basically how well is the network performing in the reconstruction task. So this is us measuring the difference between the output from the neural network to the input. But we also have this regularizer component here, which is called the KL divergence, and it's well implemented in a lot of different deep learning packages, including PyTorch. But here we're looking at the encoding component and measuring the difference between probability distribution. So this is a function designed to measure the difference between distribution functions. And altogether, this is also known as ELBO, and you'll see it comes up over and over again in papers that are variations on the variational autoencoder. So the KL divergence term is, as mentioned, measuring how much two probability distributions diverge from each other, how similar they are, how dissimilar they are. And it does make the assumption that we're dealing with a Gaussian distribution to begin with. So we have our true Gaussian distribution from our data here. So this is P, X of I. And then we have our approximate distribution, which is being learned in our latent space. So if the KL divergence score that comes out is low, then we have a better match between these two distributions here. So the actual true distribution from the data as well as the approximate one. And hence it's ideal for our loss function whilst we're trying to minimize the error that's coming out the output component of our network architecture as well. They kind of complement each other.
Can I ask a question
yeah.
here? If we can go back to the slide on the loss, for some the slide just beforehand. And just for clarification, Q sub phi, Z given X, which part of the autoencoder is that?
That's the decoder component.
Okay, and so then the P sub theta is the encoder component?
Is the encoder, yeah.
Okay, thank you.
So if we go back to, just to give you a kind of visual representation of what exactly is happening, in an autoencoder, we would have a situation where the latent space was kind of let loose and was let loose to run free. And so the encodings have kind of separated themselves into these different subcomponents within feature space. Whereas with the variational autoencoder, we've constrained it to have a unit Gaussian, and therefore they do have their own unique clusters, but you'll see some overlap. And there is a very good reason for that overlap. And the reason is because when we do our reconstruction and say we want something that's midway between these two clusters here, so say this cluster is faces with glasses and this cluster is faces without glasses, but have brown hair or something, and this cluster here had blonde hair, we can ask for an image of another face with brown hair and glasses, and it should still be able to give us something similar to what it's learned already within the architecture. Whereas here, there's not been much modeling between these different encodings, and therefore, if we ask for something in between here, it would be the network would find it a struggle to come up with something that actually looks realistic. And you see that in practice as well when we get extremely blurry images with autoencoders where there's big gaps between the knowledge space.